Okay, I think I am live. Welcome to the first recording of our econometrics class. Today, what I will be doing is talking through some of the techniques we've gone over in way of review. I'm going to go through them in a sort of flowchart method. Now, this isn't sort of a rigorous way to think about it. If you're doing an empirical project, you really wouldn't have this type of flowchart method, but I think for our purposes and thinking about the reasons and the techniques that we've used and what they're useful for, it's good to think about each of these in this way in terms of what do they give us, when are they valid, and what are the things that make them invalid. And this is going to be how we are going to talk about and how we are going to introduce the topic of instrument variables, which is the main idea and the main purpose of today's lecture. So we're going to be introducing the approach of two-stage least squares as a method for talking about instrument variables. So if you remember anything, then hopefully you remember this equation. The expectation of the error term given x is 0. This is what we have termed and talked about this semester as exogeneity. This is one of the things that needs to be true for us to use ordinary least squares. If we have this, then we can use ordinary least squares. So our first flowchart question is thinking about, do we have this? If yes, we can just use ordinary least squares. So if you've done a good randomization, you have a good experiment, then you probably do have anything else that impacts y unrelated to x. Because if x is randomly assigned, then by definition, it should be unrelated to other things that impact y. If not, then we need to start to think about why that isn't the case. The first thing that we introduced in the class was the idea of omitted variable bias. This was the idea that one of those uncontrolled for things in our error term was related to x. So our first question when we're thinking about those unrelated things related to x is it possible to just take them out of the error term and control for them? We saw this in our lab when we regressed age on your ticket amount and had a biased result, but we were able to then control for miles per hour over, and we got a different result. So if we can take things out of the error term, we can get rid of some of that endogeneity. So here is our first equation, a bivariate regression, and if you noticed, we have a prime on our error term. And we have endogeneity, meaning that the expectation of this error term, given our x's, is not 0. We know that younger people speed more, and that speed is a factor that influences tickets amounts. So therefore, the expectation of the error term given x was not 0. They're not independent. However, once we take speed out of the error term, we're getting a new error term. Once we are controlling for speed. And our hope is that this new error term is going to be uncorrelated with x. This is how multivariate ordinary least squares works. So our hope then is that we will have an uncorrelated error term and we will have an exogenous process there. We also have introduced the idea of these directed acyclical graphs as something that helps us think through looking at these things. So here is another sort of view of looking at an endogenous relationship where the error term is related both to y, which it always is, but also to our x1. What we're doing with multivariate ordinary least squares is separating out a portion of that error term and controlling for it. So we're taking from our exogenous process, separating out that x2. We now have our new error term. You notice it does not have the prime. And now this is exogenous in that there's no relationship now between our error term and x1. All right, so back to our flow chart. If we can control for part of the error term that's correlated with x, then we can just use multivariate ordinary least squares. If we cannot, then once again, we have to think about what kind of data process we have. The next sort of technique that we thought about is perhaps we can construct or have a data set that has repeated observations of the same units where they can serve as their own control. So perhaps we could see people taking exam 1 and how they studied, or exam 2 and how they studied, and the final exam how they studied. Perhaps we could see a policy and state in New York in year 1999 and year 2000. What we could use then is either fixed effects or first difference, something where we are using the states themselves, the observation units themselves over time as their own controls. If this is not the case, where we don't have the exact same units done time over time, then perhaps we have a situation where there is some sort of control group, where it's not exactly the same year over year over year, but where there are some people in a pre and post period that are a control and treatment group. And the technique that we can use with this is difference and differences. However, the important caveat that needs to apply to use difference and differences, just to remind you and reemphasize, is that the treatment and control groups need to satisfy the common time trend assumption. Meaning that if we did not have this treatment, we need our control group to be a good approximation of what the treatment group would have been. If not, then we're going to introduce and then put into context this new technique of instrument variables. Now, what we're looking for in instrument variables is a way to separate out X. Now, let me skip ahead a second. Previously, everything that we have looked at in dealing with endogeneity and dealing with this connection and this relationship between X and our error term has taken things out of the error term. Whether we're looking at fixed effects, whether we're looking at multivariate ordinary least squares, we're taking things out of the error term, and that's how we have been able to achieve exogeneity. What we're going to be doing with instrument variables is fundamentally different, because instead of taking things out of the error term, what we're going to be doing is changing X, separating X into different components. So here we have, again, a setup with an endogenous relationship where the error term is related to X and also Y, so we can't identify the effect of X on Y. But if there is something that impacts X, now let's get a little more concrete so this will make a little bit more sense. For instance, if we're thinking about the effect of a study session, and we know that the decision to go to the study session is related to a lot of other factors. Your drive to get a score on the exam, for instance. And those factors potentially also influence how much you study, how much you go to other resources. A lot of other factors are related to the study session that also impact your grade. So it's hard to tease out the causal effect of the study session as is. However, if we're able to isolate some portion of attendance on the study session, then we can get a causal relationship. So for instance, if I have your schedules and I know who, unrelated to anything with the class, simply could not attend that study session, then I can use that as a independent source of variation in attendance of the study session. What that allows me to do is break out this component of attendance of the study session, break out this X into two components. So we're using some other variable, and we're going to call this variable an instrument. And we're going to label this with Z. Z is going to be the variable that we use for our instrument. We're going to use this instrument variable to break out X into two components. One that is still problematic, still correlated with the error term, but one that is not. So your schedule is going to have one portion in terms of determining whether or not you attend the study session. Other things are also going to influence whether you attend that study session. So let's go back to the flow chart real quick. So if we don't have any of these things, then potentially we're looking for a variable Z. We're looking for an instrument. Now, again, this flow chart isn't the way you should go about things, but it's sort of a way to think about our process of learning these different techniques. This new technique we're introducing is the technique if you have a variable that can serve as an instrument. And these are actually pretty hard to find, but what needs to be true about these variables for them to be valid are the following two things. First off, to be able to help us break X into those two components, it needs to be related to X. So it needs to be something that tells us about the study session, about whether or not you're going to attend the study session. So there has to be a relationship between that variable and X. The second thing that needs to be true for us to have a valid instrument is we can't suffer from the same problem that we had to begin with. So the whole reason we're introducing this technique is because nothing else that we could figure out allowed us to reach that exogenous point of being able to identify the effect of X on Y, because there were other things that impacted Y and were correlated with X. And so for an instrument to be valid, it needs to get us out of that trap. It needs to be unrelated to the error term. So that's what this second thing that needs to be true about a valid instrument is. So let me just talk through some examples of what might give us this. Economists are often interested in the effect of attending college. Now, we know that there's a lot of factors that go into the decision to attend college, and those factors themselves can have an impact on our Y variable, can have an impact on earnings, impact on other lifetime achievements. And so the difficulty has been how to get around that problem of endogeneity. One of the ways that people have found to do that is to find variables that influence college attendance, but don't directly influence the outcome variable. One of those has been proximity to college. So if you live in a house where you're very close to a university, perhaps that lowers the sort of potential cost of attending that university and raises the propensity of attendance. So that qualifies as an instrument because we would not expect that that proximity variable would independently influence income, but it might influence college attendance. And so we can get a portion of college attendance, X, that is unrelated to the error term. Now let's go through how this works in equation form. So we've seen this broken out in terms of looking at those diagrams. I've talked you through it a little bit. So we have our endogeneity problem. We have y equals beta 0 plus beta 1x. This is our bivariate regression. And we have our problem is that the error term is correlated with x, that we don't have exogeneity there. But let's say we found an instrument z and it's valid and it needs to satisfy these two restrictions that we specified. Has to be related to x, which is the inclusion restriction. That is, there needs to be some relationship between z and x. And we'll talk about the strength of that relationship and what that gives us in our next lesson when we are talking about variance. And the second condition that we need, the exclusion restriction, is that it needs to be unrelated to the error term. That the expectation of the error term given z needs to be 0. So let's walk through how this two stages works. It works, you might be surprised, in two stages. Our first stage is that we're going to use an auxiliary regression to separate x out into two components. So our dependent variable in this auxiliary regression is going to be x, and our independent variable is going to be z. And we're going to write the error term as x tilde to emphasize that it's a portion of x that is unexplained by z. So we have separated out into two components. The second component, which is still going to be related to the other term, and this first component, x hat, which is going to be unrelated to the error term because z is unrelated to the error term. So now we have separated x out into a portion that is unrelated and a portion that is. And what we're going to do is we're going to use that independent portion of x now as our independent variable instead of x itself. In our second stage, we are using these predicted values, this portion of x that is unrelated to the error term in place of x. And y is our dependent variable. So we're using the predicted portion of study sessions or the predicted portion of college attendance as our independent variable to explain grades in the example of study session, or wages in the example of college attendance. Because x hat is now independent of the error term, we can get an unbiased estimate of beta 1. So that is it for the main part of our first lesson here on instrument variables. I'll be following up with some questions around these, with some handouts. Also, in terms of thinking through examples, I'll have some examples as well that I'll give. Supply and demand are a big one. Price and quantity, those things are co-dependent. And so getting a reliable estimate from those without using IV is actually impossible. So be looking for those worksheets from me. I will see you in office hours, and please post some questions to our forum. I will talk to you soon. Bye.